Okay, let's walk through this example as I promised, right? This is my bad the other day. I recorded, I encouraged you not to come to class. And I recorded it, and then the recording lost it. First time I think ever that's happened, where I shut it down and then it just didn't record. So I'm going to go through this example really quick, right? A lot of it is probably in another video, but I'm just going to start from scratch, just kind of flash through this. So we're asked to determine the pressures on this system right here in terms of the main wind force resisting system. So this would be if we were designing, these shear walls on the outsides or these shear walls right here. And we're only going to do it for one case, and that's going to be the case blowing from here. The total, like if you're going to do a full wind design on this, you would do one coming this way, then you would do another one coming this way, and then you do another one 0.75 and 0.75 this way, and then there's some torsion cases. That's beyond the scope of this class. That's in one of the more advanced structural analysis classes, and then in the real world. So we're just going to do it for the wind coming in from this side, hitting this 30-foot direction, right? 30-foot perpendicular, and then 60 feet going away from us, and it's 15 feet high. All right. So then we kind of went through, and in this particular case, there was not a risk to human life, so it was risk category 2. All wind importance factors are 1.0 in this case, so those are 1.0. We looked up the basic wind speed using the ASC hazard tool. This is located in Bozeman. As we looked it up, it's 107 miles per hour. Came directly from the hazard tool. The KD value, right now we're going to go through and determine all these parameters. The KD value for all buildings and the main wind force resisting system is just 0.85, so our KD is 0.85. The exposure category in the wording, right, it's open terrain with scattered obstructions, so it's going to be exposure or surface roughness C, and then you come over here and you'll see that exposure, you can read through these things if you want, but you can see that exposure category C lines up with the surface category C. So we have exposure category C. Now play in a little bit later when we're calculating some values from a table. Okay, so then we come in the topographical factor. This has to do if it's on an escarpment, right? Or like some sort of, if you build our house up here, there's going to be this like weird wind stuff that's happening there, some fluid motion, some, whatever. So there's in the text, if you end up with a case like that, we won't in this class, but if you were in the real world and you did, there'd be a way of calculating KZT. But in our case, all other cases where it's not an escarpment, then KZT is just equal to 1.0. Okay, the ground elevation factor, this is accounting for differences in pressure at different elevations, right, above, or different altitudes above sea level, right? In our case, we're at 4,800 feet above sea level here in Bozeman, and so, somewhere between 4,000 and 5,000. You could interpolate. There's also equations down here that you could calculate the exact value. In our case, we're just going to be conservative and go with the value as if we were at 4,000 feet. So we're going to use a value of 0.86 for this KE value. Okay. Then we come in for the gust effect factor for rigid buildings or low-rise buildings. That gust effect factor is 0.85. If this is to try to account for dynamic effects, that's going to be beyond the scope of this class. We're going to stick to the rigid case where G is equal to 0.85. We determined that this enclosure classification was... it depends on if you assume the doors are open or closed. We, for this particular example, assumed that they're open on one side and closed everywhere else. And when you do that, it then is considered partially enclosed. There's lots of debate in industry about whether or not it's going to be partially enclosed or partially open and things of that nature. But if you apply the code the way it is, talk to your supervisor, see how they would do it, and then if all else fails, be conservative and choose what's going to be conservative. In our case, partially enclosed would be conservative. So that would be like it was a balloon. It could be blowing one side and then it could blow up the structure, and it'd be maximizing that aspect of it, right? Versus just flowing right through it or around it. So we're assuming this thing is partially enclosed, right? For this case. All right, so then we come down here, right? So this is GCPI. That's our internal coefficients for internal pressures. We determined that it was partially enclosed. That was done right on, up here on the previous page. Okay, and so we're gonna use a plus or minus 0.55 for this GCPI value. Okay, and that'll show up in our equations a little bit later. So plus or minus 0.55. So we need those when we calculate internal pressures. Those apply to internal pressures. That's what the I is for internal pressures. Okay, so now we have to determine the velocity pressure coefficient. This is Kz or Kh. Kh is calculated at the mean roof height, right? So in our case, the mean roof height and the height of our structure or the floor that we're currently looking at are the same. So the Kz and Kh are going to be the same. But you go over to this table, 26.10-1, we have 15 feet, so 0 to 15 feet applies. We are in exposure category C, so we get a KZ value of equal to 0.85. Okay, and again, KZ and KH are equal in this case. They're the same because the mean roof height and the Z that we're looking at are both at the same height. Okay, and so then both of them are going to be KZ and KH are going to be 0.8. In your homework, that's not the case. In your homework, we're going to let this KZ vary up the height of the structure, and we would have wind loads that would look like this, that are changing up the height of the structure. And the reason they're changing up the height of the structure is because this KZ value changes with the height of the structure. Okay, what I mentioned in class, when you do your homework, the way I did it, when I was at a specific floor. All right, so if I was at a floor, I think we have a 3-story structure. All right, something like this, right? What am I doing here? All right, what I did, I think this is 15 feet. That right there is 15 feet. And then this one right here was 14 feet. And then this one was like 12 feet or something like that. So I said, well, I'm going to calculate what KZ is at 15 feet, right? So I'm going to have a value for that, 0.85. And then what I did is I went up and I said, all right, what is this thing? This is going to be at 29 feet, 15 plus 14. So this is at 29 feet, right? And so you could come over here and you could say, oh, 29 feet. You know, they don't have 29 feet, but they have 30 feet. And you could say, oh, it's going to be 0.7. What I did is I just used this equation down here. Right, I said that KZ is equal to 2.01 times Z over ZG. You can look up ZG and alpha in the table in ASCE, and then I just plugged in 29 feet and it returned to KZ. It's pretty dang close. It should be pretty dang close to, no, not 0.7. It should 0.98. It should be close to that. I was reading out the wrong ones. There's the C, and then that's 29 feet. And then you go up to the next, and so then I assumed that KZ for the 0.98 went. I calculated it here, and then so I assumed it went down there, right? That was that KZ, and then I have another KZ for this area right here. And then you're going to get another KZ from here. And what I did there is I just did the 29 feet plus that. It would be 41 feet. I think it's at 41 feet. So this would be right around 1.04, right around 1.05. Like I said, I calculated it directly from this equation. And so I calculated at the top and then used that value for the floor below. I calculated here and then I used that for the floor below. I calculated here and used it for the floor below. Right, that's what I did in the homework. But back to this example right here, there's only 0 to 15 feet, right? And in that case, KZ is equal to 0.85 and KH is equal to 0.85. Okay, so then we come down, and the next step right here is we calculate the velocity pressure coefficient. Okay, it's either QZ or QH. QH is at the mean roof height, so that's the top of it. It does not change. It's the overall height of the structure. QZ is going to vary as you go up for the different KZ values that you get in previous. That's in the homework. For this particular problem, again, there's just one thing. So we just plug in all the values. 0.00256, KZ in this case was 0.85, KZT in this case was 1.0, KD was 0.85, KE was 0.86, and our velocity that we got was 107. So you plug all those values in, and then out pops 18.21 PSF, okay? And again, QH is equal to QZ, so both of those things are 18.21. Okay, now we have that. That still is not the pressure that's going to go on the side of our structure. And also, we have to modify this by CP and G still, right? And so that's what this diagram is demonstrating right here. So these are just the external pressures, right? These are the external pressures. The external pressures is going to be the QZ that we just calculated right there, times G, which we determined earlier to be 0.85, times the CP. Well, what do we use for that CP right there? Well, that CP comes from the following table. Oh, it's just on the next page. You'll have to look up in the notes what that is, but this is just in ASCE chapter 17, or 27, chapter 27, 27, yep, 27, chapter 27. And so I'm on the wind's coming from this direction. So when the wind's coming from this direction, it is on the windward side. So if I'm trying to calculate these stresses on the windward side, the windward wall, all values of L over B. L is the length, and then that's the width, right? This is the perpendicular distance, and that's the parallel distance. In this case, all L over B's, then that CP value is 0.8. So I'm going to use a CP value of 0.8 when I'm talking about the windward wall, okay? So then I come in and say, all right, let's look at the leeward wall, right? Our leeward wall, so the wind's coming in this way, and I'm looking at this the pressures on this backside over here. So this would be on the leeward wall, right? This is L over B of, we got to calculate what L over B is. In our case, our L was 60. This is 60, and our B in this case is 30. So that's 60 over 30. So we have an L over B of 2. So leeward wall, L over B is equal to 2. CP is equal to negative 0.3. Right? So our CP is equal to negative 0.3. And so we put that down there. The positives and negatives mean something. If a number is positive, it means it's acting towards the surface that you're dealing with. So this is a positive 0.8. So then my pressure is acting towards the surface. Right? On this side over here, my CP is negative, meaning that it's acting away from the surface. Right? So I'm external, acting away from the surface. Right? And so it's just like it has it drawn right here. All right. So then we look at the side pressures. Right? Our side pressures right here, this would be side walls, right? All values are L over B, and my CP value is going to be negative 0.7. So we have negative 0.7 on the sides. Okay? So I kind of wrote them all down here so we have them in place. We'll calculate pressures in a minute. We still have to do the roof, okay? The roof, we come down, so this is roof pressures, right? We need to calculate CPs for the roof. So we just calculated all these guys, windward, leeward, sidewalls. But then also there's these roof pressures. Ours is a little bit different, right? Because our theta, we have a flat roof, right? So our pressures are going to be, straight up, right? Or straight down, right? Depending on the internal pressures and if they control or not, right? So they're going to be straight up like this. Our theta, this is the theta they're talking about. So if that theta is flat, then that theta is equal to 0. So we come down in here and we're looking at this table, roof pressure coefficients, okay? We're looking at normal to the ridge for theta less than 10 and parallel to the ridge for all theta. So this is where we're going to find our flat because our theta is less than 10 and there is no ridge, right? And so this is going to be a flat roof would fall under this category right here, right? Not up here. This would be, right? This is talking about like if you had, right, a roof that looks like this, so this would be normal to the ridge if the wind was coming this way versus, if our structure looks like this and we're blowing this direction, right, onto it this direction, what that CP value would be. In our case, it's just flat, right? It's just flat when the wind's coming in there. And so it would fall into this category. We look at H over L. Our H, in this case, is 15 feet. Our L is 60 feet. So our H over L value is 0.25. Right, so it would fall into this category right here. My H over L is less than 0.5. It's 0.25. And then our CP value is going to change at different locations. It's going to be from 0 to H over 2. We're going to have a CP of 0.9, negative 0.9. From H over 2 to H is going to be negative 0.9. From H to 2H, it's going to be negative 0.5. And for all values greater than 2H, it's going to be negative 0.3, right? You'll notice that they give us two values. There's these guys and these guys, right? Technically what that amounts to is two different load cases, right? And so there's a maximum amount of pressure and then a minimum amount of pressure. That has to do with sometimes a minimum amount of pressure will actually control the design of certain elements. Actually, the internal pressure that's pushing on the thing, or the uplift could actually help you. It's kind of hard to think about, like if you're designing a rafter, that having that uplift from the wind actually helps you, because if you had like a truss that was carrying, if you had some sort of truss that was carrying loads, and you have your snow loads, for instance, acting down like this, and then you have these wind loads that are acting up like that. And so actually having more upward wind forces would actually help you in your design. And so to count for maybe the wind isn't causing that much of an effect, they put in a maximum and minimum. We're just going to deal with the maximums. We're not going to treat these would be completely different cases in the overall grand scheme of things. We're just going to deal with these numbers right here. Okay, don't worry about these second numbers. These have to do with, those are the minimum amount of wind pressure that can be there. And I make a little note about that over here. Okay, so that's what we got. So basically, like I said, here's a summary of what I just said. From 0 to h over 2, from 0 to 7.5 feet, CP is equal to negative 0.9. From h over 2 to h, so basically from 7.5 to 15 feet, again, it's just 0.9. From 15 to 30, that's from h to 2h is negative 0.5. And then the rest of the structure is just CP is equal to negative 0.3. Okay, all right, so now we have all of our CP values. Now we come into the next section. 27.3.1 says this is how you calculate your pressures on the structure, right? And so you have this component, P times GCP, Q times GCP. Q is, in this case, the QZ that we calculated up above, right? On the windward, if we're talking windward walls, right? Or even just the external pressure, it could be Q, or it could be QZ or QH, depending on what we're looking at, and I'll apply it down here. G is that same factor, is that gust factor that we had before, which is 0.85, and then CP, again, depends on where I'm looking. If I'm on this wall, or am I on this wall, or am I on the roof, or am I on the sides, right? My CP is going to vary based on that. So that's the external pressure. All this first part of the equation is the external pressure. This part of the equation is the internal pressure, right? And this could either be the building being blown up like a balloon, or the building being sucked down like there's a negative pressure on the inside sucking down like against the walls internally, okay, pulling kind of on the inside of the structure. Okay, and so the total pressure is going to be the external pressure minus the internal pressure, right? And it's important to keep track of your signs if you're going in here. If things are negative, if it's negative internal pressure, this will be a negative value, and it'll get added on here. We'll watch it play out. Okay, so the way for this particular example here, I kind of calculated them separate. I said, what is the internal pressure? What is the external pressure? I'm going to calculate this on each one of my walls, and then I'm going to calculate the internal pressure, and then I'm going to sum them together. Okay, so if we looking at the elevation of the structure, so looking at it from the side, okay? If I'm looking at it from the side and I'm looking at the windward wall, right? The wind's coming this way. I'm looking at the windward wall. I'm going to use the QZ value. In our case, is just one of them. QZ times G, which is 0.8. So 18.21 is what we calculated for QZ. 0.85 is what we had for G. And CP for the windward wall, we determined to be 0.8. So right here, right, we determined that to be 0.8. Right? And so you just calculate that. 18.21, 0.85, 0.8 is 12.38 PSF. So the pressure on the side of my windward wall would just be 12.38 PSF. So that's the magnitude of this pressure on the side of my building. Okay. I then go into the leeward side of my building over here. Okay. My leeward side of the building. For calculating the leeward, it's going to be QH, not QZ. It's going to be QH times G times CP. Right, QH is QZ in this particular case. It's going to be 18.21. Your homework, it's not going to be the same. QH is going to be constant. It's just one value. It's at the height of my structure. G is going to be my 0.85, and my CP I determined to be negative 0.3, and so I get negative 4.64 PSF. So I get 12.38 on this face and negative 4.64, the negative meaning that it's pulling away from the surface of my structure. Okay, across the top of my structure, this is where it varies as I move across, right? So this is from 0 to 15 feet, kind of what we had up above, right? It's going to be negative, so again, it'll be the 18.21. We determine my G to be 0.85 and my CP to be equal to negative 0.9. So I just calculate, multiply this by this by this, and I get negative 13.93. So that's over the first 15 feet. Right? That's from 0 to h over 2, and h over 2 to h gets me 15 feet. Okay, then from 15 to 30 feet, I'm going to have a CP value of equal to negative 0.5. So at 18.25 times 0.85 times negative 0.5, and I get negative 7.73. So the magnitude, that's the magnitude right here, right, is the negative 0.5. And then from 2H for the rest of it, all the way to, what does it end up being, 4H, I guess, it's going to be 18.1, and it's going to be a negative 0.3. So when you carry all that out, we get negative 4.64. So then my roof uplift, the uplift on my roof is going to be 13.93, 7.73, and 4.64. Now that's just for the external loads, right? So I got the pressure here, 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 and here, right? And that's just for external. there's also the internal stuff happening. There's this part of it. Okay. And so again, that internal pressure could be going both directions. It could either be sucking in like this, right? It could be sucking in like that. That would be considered a negative internal pressure because it's acting away from the surface of the inside. Okay. Or you can have positive external pressure or internal pressure where it would be pushing out, right? Like blowing up a balloon. Right? And you have to check both of those cases, right? Okay. So what I did down below is I said, okay, now let's take and combine these two things, right? The internal and the external, right? So my internal pressures, I did right here. It's plus or minus 10.02. So to calculate my internal pressures, I use my QH, in this case the same as QZ, which is 18.21. GCPI, we calculated, right? That was up here. GCPI. That's what GCPI is for the internal pressures, plus or minus 0.55. Right? So 18.21 times 0.55, so I get 10.02 PSF, right? And it's either going to be a positive or a negative value. So I'm going to do it once for positive internal pressure. That means it's acting out, it's acting towards the surface of the inside, right? So it's pushing out on this thing, okay, as the arrows indicate right here. And so then you work it out. So I've got 12.38 is what I calculated for the external, right? Right here, I got 12.38 is the external. And then, but the internal, that pressure is acting in the opposite direction, right? I got this guy, and so they're acting opposite direction. So it's going to be 12.38 minus 10.02, right? And technically, if you keep track of your signs, 12.38 is a positive, right? It's a positive external pressure. And then this equation up here says you minus the internal pressure. And then you're minusing the internal pressure. That internal pressure is a positive number. So 12.38 minus 10.02 gives me 2.36. So my resultant pressure on the face over here is 2.36 PSF. If you then go over to the other side here, right? I calculated it to be 4.64, right? Negative 4.64, just to be consistent there. Okay. And then negative 4.64 minus the internal pressure. The internal pressure is considered positive, right? So negative 4.64 minus the 10.02, right? That's a positive on the inside, but you're subtracting it according to that equation up above. So you get 4.64 minus 10.02. So negative 4.64 minus 10.02. And so I get a negative 14.66, meaning that my resultant is going to be at 14.66, right? So I have 2.36 on this face and 4.66 on this face over here, right? And so that's my internal and external together, Same thing on the roof up here, right? This is a negative, 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 and I'm subtracting a positive value for each of these, and so they end up adding on, right? You could see that too, like this guy plus this guy would give me this. So this would be 10.02 plus what I calculated up here of 13.93. So I should get 23.95, right? And then same thing here. This value, 17.73, is 10.02 plus 7.73, right? And then this is 14.66 is this 4.64 adding on 10.02 gives me this one right here. Okay, so that's for the side. Then you come down and you do the internal pressure, right? And so the internal pressure it's now sucking inward. And so on the left-hand side, these guys get added together. On the right-hand side, these things, we come up with a difference between what it was for the external pressure up here and what the internal pressure is down here, because they're acting opposite directions. Okay, and again, if you keep track of your signs throughout, it works itself out, right, on which way it's going to be moving. Right, so for your spreadsheet, just taking external pressure, be careful of positive negatives. Your internal pressure, be careful of positive negatives. Do your external pressure minus your internal pressure, and it kind of all works itself out. Okay, and so basically, again, what this one is just doing the same thing, adding the things together, subtracting them. It's just now thinking about my internal pressure acting in the opposite direction. Instead of blowing out like this one, it's sucking in on this one. Okay. Right? So these would be two cases that you would have to design for, right? One of your load cases is you would set it, you would say, here are my loads on my structure, and then here are my loads on my structure. And you'd have a load case that's positive internal pressure and negative internal pressure. And who knows, what controls this overall design, right? It gets pretty convoluted trying to keep track of what it is that's going to control. Okay. And then I guess just to close the loop here for the winds coming in this way. Now I'm looking from the plan view, so I'm looking down on it. I'm looking down this direction on it, and then I just wanted to show this external, the sidewall pressures. Right, same idea. This is going to be the 2.36. So this is for the positive internal pressure. That's this guy, right? So this 2.36 is on this face right here. And this over here, this 14.66 is on this face right here, right? And then to the sides over here, that's just going to be my QHG times CP. CP for sidewalls is 0.7, so we get this to be, 10.83 is what that says, 10.83. Right? And so when you have internal pressure, the side pressure is going to be that 10.83 plus the 10.02, which gives me the 20.85 on the outside. And then you come down here and you have the 10.83 is the external sidewall pressure, but then you subtract out the internal pressure, and so you get 0.81. So your sidewall pressure is 0.81. Okay? And that's kind of where we left off. Then we calculated the base shear, right? You can calculate the base shear from this. You take that pressure and you multiply it by the area in which it acts. So that pressure multiplied by that area, which is 15 times 30. And then this backside over here, you have, actually this is the case here. You have 14.66 times that area, and you get 76.59, okay? Or you could do it for this one. This one and this one, you should get the same pressure. You should get the same base shear, because the difference is, are these acting in or out? If they're acting in this particular case, since it's symmetric, right, what's happening there is canceling out what's happening on the other side. If it's acting this way, they cancel out on the other side as well. So the internal pressure doesn't affect your base shear if it is uniform. If it had some sort of parapet where one side had more pressure on it than the other side, then they don't necessarily cancel each other out. So cool. All right, hopefully this saves. Good luck.